In this problem, we have an interesting situation where we have a race car that we're trying to measure the speed of, and we're measuring its speed by sending it one direction down a distance d, and then sending it back down the other way, the other direction across the same distance. And the car will be timed both times. Now, what's interesting about this problem is that there is the presence of wind, which I've represented with these blue arrows. So this is V sub W as defined in the problem description. And if we assume that the direction and speed of the wind is not changing, then that means that as the car is traveling down one direction, the wind is helping the car, basically pushing the car further along its motion, increasing the car's speed beyond what it would have been in a windless situation. But while the car is traveling the other way, it's fighting against the wind, so the speed of the wind is pushing against the car's speed. So the problem's asking us this: if we take the car's speed if we measure the car's times in both directions, and we know the distance d, then how do we figure out what the car's speed would have been in a windless situation? And the problem proposes two different methods and asks us to figure out which one will work. The first method proposed being that we find the average of d over t sub 1 and d over t sub 2, basically taking the effective speeds that we measure and adding them together and dividing by 2. Or method 2, which is just taking the distance once and then dividing by the average of the times. So just taking d and dividing that by the sum of the t's divided by 2. Let's try just going through this situation logically and figuring out what's going to happen. Just for the sake of defining our variables, let's say that the measured time interval t sub 1 is for the case when the car is traveling with the wind, and we'll say that t sub 2 is the time measured for when the car is traveling against the wind. For the t sub 1 part of this scenario, let's say that the car's actual speed, let's call it the effective speed. Let's call it V effective 1. And the reason why I'm saying the effective speed of the car is because this is the speed that the car will actually be moving at because of the wind. So V effective is the effective speed because it takes the wind into account, and not just whatever is on the car's speedometer. Or rather, just whatever the car's speed would have been in a windless situation. And similarly, for the T2 case, we'll say that the car's moving speed is V effective 2. Now to write this out more mathematically, again, when I say V effective, that's the sum of the wind speed plus whatever the car's windless speed would be. So in the t sub 1 situation, where the car is moving with the wind, again, the speed of the wind and whatever the windless speed of the car is are helping each other. They're pointing in the same direction. Those speeds are adding together. So V effective 1 is going to be the wind's speed, V sub W, plus V sub C, which is the variable defined in the problem as whatever the car's speed would have been in a windless situation. So whatever the car's speed would have been is being added to the speed of the wind to create the actual effective speed. Similarly, for the T sub 2 case, the speed of the wind is impacting the car's motion, only now, since the car is moving in the opposite direction as the wind, they're going to be negating each other. So the effective speed of the car in part 2 is going to be the car's windless speed minus the speed of the wind. So V sub C minus V sub W. The other variables that we know in the problem are d, the length of the track, and t sub 1 and t sub 2, which we assume are measured. Which is important to keep in mind because remember, these effective speeds are the speeds that are actually being measured, and speed is equal to distance over time. So V effective 1 should also be equal to the distance of the distance d divided by the time t1. Similarly, V effective 2 should be equal to the distance d divided by t sub 2. So we now have these two speed equations that we're going to want to try and do something with to cancel out the wind speed. We're looking for a formula to describe the speed of the car without the wind. And we can do this using equation addition. Notice that one of our equations has a positive v sub w, and the other equation has a negative v sub w. So if we add the two equations together, then those v sub w's will cancel out. So we have v sub w, or v sub c, plus v sub w equals d over t1. And we're adding to this v sub c minus v sub w equals d over t sub 2. We're adding these two equations together. And we can see that the v sub w's will cancel out. V sub c plus v sub c is equal to 2 v sub c. And then d over t sub 1 plus d over t sub 2. That is just, there's no way to simplify that right now. Just d over t sub 1 plus d over t sub 2. So to solve for the car's windless speed, v sub c, we can just divide both sides of the equation by 2. So we find that v sub c is equal to 1/2, that's because we're dividing by 2, of d over t sub 1 plus d over t sub 2. Notice that there is no v sub w in this equation. This equation has no representation of the speed of the wind, which means that this is an equation for the car's speed completely independent of the wind. And going back to the problem statement, which asks us which of the two methods is better, we can see that the equation we've just found corresponds to what the problem describes as method 1, where we find the average of d over t1 and d over t2, and find them as an average. And that's what we're doing here. We're taking d over t sub 1, adding it to d over t sub 2, and then taking the average of the two options, of the two terms, by dividing them by 2. So this equation represents method 1. So method 1 is the better method. That's the method we need to use. Alright, so part B of the problem is, I'm going to be honest, it's pretty hard. It's actually really hard, in my opinion. Part B of the problem is asking us to find the fractional difference in the two options, the two methods. So let's say that, just to define some variables real quick, let's say that VC is the variable that represents the answer we'd get from method 1, which we just established is the more correct method to use. And let's define another variable, v sub c prime, which refers to whatever answer we'd get if we used method 2. The problem is asking us to find a fractional difference between the two methods. So what that means is the difference between the two methods, so v sub c minus v sub c prime, divided by the one we know actually works, v sub c. This fraction right here is what we want to find, but in order to find it, we need an expression for v sub c prime. So let's investigate method 2 now. V sub c prime. So according to method 2, the method proposed in the problem, we would take d and divide it by the average of the two times. So we're taking d divided by t sub 1 plus t sub 2, all divided by 2. First off, let's begin our simplification by bringing this 2 into the numerator. So this becomes 2d divided by t sub 1 plus t sub 2. We don't actually know the time values, so recall that when we have a constant speed, time is equal to distance divided by speed. So the time variables in the denominator here can just be replaced with d divided by their effective speeds, like this. And notice that now that we have a d in every single term, those d's can be canceled out completely. Notice that our denominator is still pretty messy, so we're going to use the least common denominator cross multiplication method to clean this up. Like this. Notice that in our denominator's numerator, we have a negative v sub w and a positive v sub w being added to one another. They can just cancel out. and notice that we have a v sub w plus another, or v sub c plus another positive v sub c. So those two can just add together. And notice that this leads to a 2 that we can cancel out. And lastly, we can simplify the denominator's denominator by applying the FOIL method of binomial multiplication. Referring to the FOIL method, where we multiply the first together by the inners, by the outers, and then by the last, and then add those terms together. And then this is what we end up with, v sub c squared minus v sub w squared. Finally, we'll bring the denominator's denominator into the full numerator where the 1 is, because that's how fractions work. And we ultimately end up with v sub c squared minus v sub w squared, all divided by c. Now finally, we are at a point where we can plug this in, because remember, this what we just found is an expression for v sub c prime. We now are at a point where we can plug this in to the fraction, the formula we discussed earlier for the fractional difference that we're trying to find, of v sub c minus v sub c squared, or v sub c prime, all divided by v sub c. Now we're going to plug in what we just found. So v sub c minus, and then v sub c prime, that is v sub c squared, minus v sub w squared, all divided by v sub c, and then all this is divided by v sub c. First off, this all still probably looks pretty unclear and messy, so I'm going to separate this whole thing into two different fractions, with the v sub c as a denominator for each of the different terms. Like this. Notice that v sub c divided by v sub c is just 1. And for the second term, we can combine the v sub c's together into a squared. Like this. Once again, though, I'm going to take this second term and separate it into two different fractions. Like this. And notice that we have v sub c squared divided by v sub c squared, so that just becomes a 1. And then notice that by subtraction, these 1's will cancel out, and these negative signs will cancel out to leave the remaining term positive. And finally, we end up at a very simplified term of v sub w squared divided by v sub c squared. And remember that if you have something squared divided by something else squared, you can remove the square and apply it to the entire fraction. So really, our most simple result is v sub w divided by v sub c, all of which being squared. This is our ratio, and the reason why we went through all that trouble, all those steps to get to this point, is because the only information, the only numerical information the problem gives us is the ratio of the wind speed to the car speed. We're given the ratio of v sub w to v sub c. That is all we are given numerically. So in order for us to find this ratio, we had to do the steps required to get us a term that included a v sub w to v sub c fraction. And that is what we have found here. So all that is left for us to do is take the fraction that was given to us, the ratio that was given to vw to vc, 0.0240, and square it. Put that into a calculator, and we find this to be equal to 5.76 times 10 to the power of negative 4. And that is our answer to this problem. And that is it for this problem. I hope this video helped you out. If it did, please consider subscribing, as that'll help me out in making more videos just like this. Man, this problem was tough. But that's all. If you have a question or a request, leave a comment down below, and I hope you all have a lovely day. Bye-bye.